Okay, good evening once again, everyone. So today we are going to take a look at more of linear regression. Last Monday, we had started off talking about linear regression. We spoke about the process of training a model, and we spoke about data processing, pre-processing. And then we looked at the 5 stages of training: data input, forward propagation, loss calculation, backward propagation, and parameter optimization. Today, then, of course, we did a bit of linear regression with single variable. So in this case, I was manually adjusting the parameters. So you remember we tried to simulate or predict the values of a system of data points, the values of data points based on a linear equation, which is really what linear regression is. It's a statistical method. We use a straight line to model the relationship between a single independent variable, which we call x, and the dependent variable, which we call y, whose value comes from the value of x. And then the specific value of y depends not only on the value of x, which is the independent variable, but it also depends on the parameters around x, which include m, that we call the gradient or the coefficient of x, and c, which is also another coefficient, but it is a constant. So by adjusting the values of m and c, which is what we actually call the training process in machine learning, in this very simplistic example, we were able to adjust what the model will predict as the y, depending on what value comes in as x. So in this case, the model is actually this single linear equation, y equals mx plus c. That is the model and nothing more than that. So when you hear machine learning model, it's basically a system of linear equations, like I have said, and each of the coefficients in this linear equation or this system of linear equation is what we call the parameter. And and lots of them will make up all of the parameters. Of course, what you'll be asking yourself now is how can, this number of, a large number, how do these parameters even come together to make sense and learn a complex thing like, AI, composing a poem or a letter or, doing some playing chess, all of that. So that's part of this interesting journey of machine learning. How do we move from this single linear equation, y equals mx plus c, to ChatGPT? It is an interesting, question, and we're going to see that. So with linear regression, you are basically using a single straight line. That's why it's called linear, to predict your models. The model in this case is the equation, the straight line equation. That's the model. So you use that to predict a value, right? So the best way to do that is you look for a straight line that is going to minimize the error, of prediction versus the actual value. So for you to do that, you have to first of all create what we call a loss function or a cost function. Those are the terminology that is used. So the cost function will calculate the difference between the predicted value and the actual value. So what we call the error. So that error, there are different types of loss functions, right? Or cost functions. In both cases, they mean the same thing. So you have a mean squared error as an example, right? That's one. And I explained how that works. It's basically the average of the sum of the squares of the error or the difference between predicted and actual for each data point. So that is what this function is basically. It's a summation across all data points. The all data points are from I being 1 to I being n. So I is the I here, yi, right? Minus mxi plus c. So remember mx plus c is y hat. if you look at the previous one. Y hat is a terminology we use for the prediction that comes out from the model. So you calculate that difference for each data point. That's why you have the i's. The I represents a single data point. So for n data points, which is the total sample of data points that are given to you as part of the training data, you square, right? Then when you square, you sum it. That's what this summation symbol stands for. And then you divide it by n, which is again the total number. So when you divide a sum by the total number of samples, right, or of items in that sample or data points in that sample, what you get is an average or a mean. So that's why this is called a mean squared error. You also have MAE, which is the mean absolute error. So the mean absolute error, instead of squaring inside this summation, you take the absolute value, which the absolute value is basically ignore the sign. Whether it's positive or negative, forget the sign, just take the value, which is the number, which obviously means you only take the positive value and you sum it up. So the essence of using squares, like I said before, or using absolute, is we don't want negative and positive errors to cancel each other out, because we are not trying to calculate the sum of the errors. We are trying to calculate the magnitude of the total error in the system. So you have to remove the sign so that they don't cancel each other out. So when you do that, you get this equation. Now your goal is you want to train this model so that you minimize this total error as measured by the mean square error or any other um, cost function that you choose. So to minimize this, right, you will now adjust the parameters in the model, in this case, the M and the C. And if you were to plot a graph as you are adjusting the M and the C, which in this case are the weights, you would see that the error drops at up to a certain point. At a certain point, it hits a minimum value. But if you continue adjusting it, the error begins to increase back. So what that means is that there is a point of minimum error. That is the goal. Your goal is you want to get to that point of minimum error. So what is the next step? There are two ways to solve this kind of linear regression. The first one is the analytical method, where to find this minimum point, you use the simple mathematics that we have learned, right? Which is the point of inflection, or the minimum point, is a point where the change in the cost function, or this gradient, is zero. The gradient of the cost function itself, not the gradient of the predicted value, or not the gradient of the model of the line that you are using to predict. No, not that one, but the gradient of this cost function, right? At the point where it is zero, that is represented by d delta j delta m, or del j del m, you get zero. That is the gradient. So the only thing is that we use a partial differential approach, because it has been proven that you only need to adjust each parameter to a point where its own contribution is the minimum. So if each parameter you adjust to a point where each parameter's own contribution to the error is a minimum, you would have successfully minimized the entire error in the system. So you don't need to consider the we assume that these parameters are independent. They are not coupled in any way, mathematically or otherwise. So we can adjust M to a point where the change in the cost function with respect to M is zero. And we do that math. We can also adjust J to a point where the change in the cost function, which is del J, with respect to the constant C, which is the second parameter, is also zero. So this curve applies to both the M and the C. So you can actually see that even though it's written weight here, but this same curve applies to the JDM to M, right? As you're adjusting M, it gets to a point where the cost function, which is on the y-axis, becomes at the minimum. And at that minimum point, the rate of change of that cost function with respect to the M parameter is zero. Same thing with C. So this curve applies to both. Now, what do you do? The next thing is you take this formula and you do the necessary maths with it, right? Unfortunately, I do not have enough time to go into the maths of this, and I'm not really going to go into it because that's not really the purpose of our training. Our training is not for you to learn regression using analytical methods, which is what this is, right? But rather using numerical methods, which is um, iterative adjustment, right? And that is, for example, what gradient descent will do for you. So I'm not going to go into the maths of it, but just take it that by the time you take the the derivative of the cost function, right, and set its value to 0, and reverse calculate the m, you are going to get this formula. You make m the subject of the formula. You are going to get m. You're going to get this formula for m, right? You can actually see that here, right? If you do a derivative of this, and I'm going to show you this in another slide, but if you do a derivative of this, it's going to give you 2yi minus mx plus c in brackets, right, times x. So it's going to be 2xi yi minus 2xi into yi minus mx plus c. So that will give you an equation which, when you make m the subject of that formula, you're going to get m as n times summation of xi minus summation of xi times summation of yi over n times the summation of xi squared minus summation of xi all squared. So again, it would have been interesting for me to delve into this, but I'm going to spend a lot of time, and today is jam-packed. But just understand, you can go do it as an exercise on your own, right? That by the time you take this first equation, where we say del J del M equals to 0, you do the derivative, the partial derivative. This del, by the way, we call it del, is just short for delta. I could have said dj dm, but dj dm is where you have a single variable, so it's a derivative. But when you have partial derivatives, we typically use this other d. Instead of a straight d, we use this. So this formula, by the time you do that derivative, like I said, make it subject formula, you get this for m. So you can now slot in all the values of x and y and do this calculation, and you will solve for m. This is what we call a one touch, right? Or a one shot. It is a one shot, right? So the one shot it means you calculate the correct m, the minimal m, at a single go, right? So that's one benefit of using an analytical method. You just do a single calculation. You don't need to do iteration, right? But you also see where the iteration is more powerful than this. We'll talk about that. So similarly, if you also take this second differential equation, where you are calculating the contribution of the C constant to the cost function, which is del J del C, and you take the derivative of this J with respect to C, you are going to get 2 into yi minus mxi minus C, right? That's all you get. So you can then flip it and make C the subject of the equation, and you get this back, that C equals summation of yi minus m summation of xi over n. So this gives you a single equation for you to do a one-shot calculation of the C, right? Which is the second parameter. That is linear regression using analytical methods, like the mathematical equations that we were used to. Now, this works well if you already know the cost function, right? So I can actually do this, and it's really nice. I can do this, right? You can even use this and program it in a computer because you already know the equation to use. you know you are using a cost function of mean square error, because the mean square error that is going to give you this derivative when you flip the formula, right? But if you use a different one, it will be a different thing. So in this situation here, we use our same analytical method to just slot in the values into those equations that we had. And we immediately calculated that C, for these 3 points, X and Y points, C is 1.214. Sorry, M is 1.214 and C is 0.19. And you can slot that to get your equation. Y equals 1.214X plus 0.19. This is the model. In fact, you can consider this as the trained model. It has two parameters, 1.214, which is the M, and 0.19, which is the C. And this is the values of this is the values of the two parameters that will give you the least error. So you can say with this, I can do a good prediction. I am using this very simple case to explain so that when you are visualizing in your mind, what is a model? What does parameter mean? What does it even look like? Like people have been asking, you know that these are just floating point numbers, like I said, that have been adjusted by training. Now, here it is, we just solved it one shot and we got the answer. But there is a downside. For really complex systems, you cannot come up with an equation that does that. Or if you were to come up with such an equation, it would take too long to calculate, even with the fast computers we have today. So we come up with a second approach, which we are going to talk about. By the way, this is a visualization of the results. So this is a good example where, well, this is not actually exactly this data point, but this is it. Now, yeah, I did a hands-on session where I tried to explain how we could do this, right? Using a manual process of adjusting the parameters, but I'm not going to do that. Rather, what I'm going to show you is a a Jupyter notebook I had already done, right? Which kind of does that linear regression. So you can see all of this. It does all of that, right? And you can see that we are just using this equation to calculate, right? And this equation can work for any one. This equation for calculating the optimal M and the optimal C is actually based on the root mean square equation, and it is called the normal method or the normal equation, right? The method of calculating by using an analytical equation, a mathematical equation that you have essentially created. That's what we call the normal equation or the normal method. So with this one, you just use a single equation. As long as the cost function that you used is a mean square error cost function, this equation will always work and will always give you the correct optimal values, which you can then use for your prediction, right? So I'm going to share this Jupyter notebook at the end of this class, and then if you like, you can play around with it. This is basically what it is. And you can see this is the same graph that we have done with these 3 points that have been fitted, right? Now, so I think I had given everyone a set of data points. This is the set of data points I gave before. For this set of data points, right, you can also use this same set of data points to use the normal equation to calculate it. So that will be the task I'll give to you. You will calculate using the normal equation and you show me that in your Jupyter notebook. Now, after that, like I said, this is not what we use for machine learning, because that is not actually learning. Well, in a way, it's learning. You've calculated the parameters one shot. It's only two parameters, so it's not going to take a lot. It's only two parameters, and it's only two variables, right? The two variables, the independent variable X and the dependent variable Y. So only two variables and only two parameters, M and C. So it's very easy. If you pull that out into a matrix, it's a single vector, right? In fact, it's a single scalar and a single bias. Okay, so maybe a single vector. But when we go to more complex stuff, it becomes more difficult. So in that situation, we use other approaches, right? Iterative means of, gradually adjusting the parameters until it gets to what you want. One of these iterative approaches is what we call gradient descent. And we're going to talk about gradient descent. It's an optimization algorithm that you use to find the minimum of a function, right? So typically, of course, is the cost function. And the cost function, like I said before, is a measure of how close your prediction is to the expected or actual value, right? It measures that error. The smaller the error is, the smaller the cost function, the value of the cost function, or the result from the cost function, the smaller the error, right? So what you now do to reduce the error, right, is to adjust the parameters iteratively, over multiple steps. And to do this, right, you calculate the gradient of the cost function. You can see that when we were doing the the mathematical analysis or analytical method, the normal method, right, we actually did take the gradient and we found where the gradient is 0. And then we reverse reversed the subject of the formula and we calculated parameters. But in gradient descent, you don't do that. You will still take the gradient, but you take the gradient at that point currently where the parameters lie. When you take that gradient, what you now do is what we call the direction of steepest descent, right? You go in the opposite direction. So you are essentially calculating that I want to reduce. So if the gradient is positive, that means I want to reduce the weight. If the gradient is negative, that means I want to increase the weight. This is very easy for you to see it here. So let me annotate this so that it will be very easy to understand. So let's say I choose a point, right, in this space here. And this is the point, right, where my prediction currently lies. Remember, this graph here is a graph of the cost function. It's not a graph of the equation. It's a graph of the cost function. So what we are saying is that at this point, right, if the weight is at this value, let's assume the particular weight that we are adjusting, let us assume that it is M, right? So we are adjusting M. M is here, right? And the value of M is at this point, let's say maybe minus 3.1, right? Okay, minus 3.3. That's kind of approximately where M is on this, on this point. So for this M, we will get a corresponding value of the cost function or the error, right? That corresponding value of the error, we'll get it from here. So on this axis, what you have is the error. And so let me annotate that here, right? So that is the corresponding value of the error J, okay? So we have M and we have J, right? Now, let's assume the value of J is 10, 20. Okay, let's still assume 0. Yeah, let's say 0.2468. So this is 0.69 or 0.68, right? So that's the corresponding value here, maybe 0.69. Okay, so at this point here, I am here, and right now my cost function at this point is 0.69. So the gradient at this point, if you want to calculate the gradient of this cost function, it will be something like this, right? So that gradient that we have calculated, it will be something like this. In this case, the gradient is negative because it's going downwards. A positive gradient goes upwards. So a positive gradient goes this way, right? But a negative gradient goes downwards. So the gradient is negative. So because the gradient is negative, what does it mean? It means I have to adjust the parameter in a positive direction. I have to adjust the value of the parameter in a positive direction. So what that means is gradient is negative. I have to adjust the parameter in this direction. That's a positive direction for me to reduce the error. So let's assume I adjust the parameter in a positive direction arbitrarily, right? So I adjust it to this second point, which is a bit better than the first point. So I'm going to use this. So I adjust it positively to this point. Yes, I have to change the shape. So I adjust it to these points, right? Let me draw the upward line. So I adjust it from m equals minus 3.3 to this point where m would be maybe minus 2, right? So in this point here, I have adjusted this parameter, let's say m, to where its value is 2. And in adjusting it to where its value is 2, you will see that the error has gone down, right? So this is m being 2, the green one, right? So we have that, and then we have this, and this will be the value at this point, right? And if I then take that value at this point and I draw the corresponding value on the cost function side of it, so you now have that the cost is going to be lower. So we'll have J being about, let's say, 0.23. Okay. This is what it is when we say when you say, okay, we are doing gradient descent. That's why it's called descent. You are essentially descending in this curve. You continue descending by adjusting the parameter m from a value in the opposite direction to the gradient so that the gradient will reduce. If you adjust the parameter in the same direction to the gradient will increase. But if you adjust it in the opposite direction, so in arrows, shows because the gradient is negative, we adjust the parameter positive. So we adjust in the opposite direction. That adjustment will bring us closer to the minimum point. Now, it is iterative. So let's say the first adjustment, I adjusted it to minus 2.0. It is still not yet at the minimum point. So I do another adjustment. Sometimes you can overshoot. So like if you look at this graphic here, we are actually adjusting in small, tiny increments here. We don't always want to adjust by, that's why you don't do gradient descent with large increments. If you jump with large increments, what do you think will happen? What will happen? Let's try that with maybe a blue line, right? If we try that, what you will see is that we will cross over this point of minimum and we will end up somewhere where it is higher, right? We'll end up somewhere where it is where the gradient, we have gone past the point of minimum value and we are now going beyond. We are now increasing the cost, right? We're now increasing the cost. So you don't want to do that, right? You don't want to do that. So what you do is small changes. But let's assume you do happen to, cross over that minimum point, okay? And you get here, right? You are not at the minimum. Even though in this situation, the cost function is actually less, right, than the previous cost function, but this is not the minimal value. You have crossed over to this side. But the interesting thing is that on this side now, the gradient has now switched from being negative to being positive. So this is now the gradient at this point. This gradient is going upwards, right, up and to the right. So it's positive. So what that means is that your adjustment will be the opposite direction of the gradient. And since the gradient is positive, your adjustment will be negative. So you will now have to go backwards. You have to go backwards and adjust your parameter backwards. So that will bring the parameter close to, um, closer to the minimum point. So this process, you continue iteratively, you adjust in the opposite direction to the gradient. If it overshoots, you go in the opposite direction. At some point, this thing will be bouncing around essentially, right? That's essentially what's going to happen. And that's what this is kind of, indicating. Like you are bouncing around, you are just bouncing around like that. Let me clear this so that we can see everything again, right? So you see that you just be bouncing around. Let me look for a nice color for bouncing around. So you just be bouncing around like this. And then if you happen to overshoot, you bounce back, right? And if you overshoot again, you bounce back. And you keep going back and forth until at some point you will end up right here. And at this point, you will, no matter how many more iterations you do, your cost function will never go lower because this is the minimum. This is the lowest value of the cost function that you can ever achieve. Therefore, no matter how much you bounce around, your cost function will always be this. By the way, this line doesn't mean that the cost function is zero. It just means that the cost function is at its lowest. Sometimes it can be zero, but the only time the cost function will be zero is if in a case of a linear equation, the 3 points are exactly lined up in a straight line. Okay. So this is an intuitive graphical, explanation of gradient descent so that you understand what it is and the principle. And for your information, you do this for each of the parameters, right? The only thing is that you are doing it for all the parameters simultaneously at the same time, right? And that's where machine learning is really excellently done using graphical processing units or GPUs, right? Because they can do this gradient descent or any other optimization algorithm multiple times for multiple parameters simultaneously. Okay. So with that, we now look at the mathematical formulation of gradient descent, right? By the way, before I move on to it, the only other approach that you can use to solve a numerical regression like this, a linear regression, is what we call the normal method, which is what I showed already. That is basically coming up with a mathematical formula and then using that mathematical formula to calculate the minimum value with one shot. This one is many shots because you see how each time you are bouncing around, you are doing an operation, you are doing a calculation. So you probably may need to bounce around a lot of times before you get to the minimum point. But with normal method, no matter where you start from, in fact, you don't start from anything, you basically don't have any value. You don't have a starting value, normal method. You just calculate it and boom, you have your minimum value. So, but the problem with normal method, like I've already said, is when your data set is very large, when you have millions of rows and columns, which I'll explain later, each row is a data point, each column is a feature, right? And we'll talk about that when we get to regression with multiple variables. When you get to that kind of situation, normal method becomes very, very complex, right? It becomes very difficult to do. So um, for complex models like neural networks, for large amounts of data, the gradient descent is far more effective, is more optimal, is better. But for small models that only have a few parameters, 5, 6, 10 parameters, the normal method is better. So this is how it works, right? I've already kind of explained it already in the previous slide, but I'll go through this quickly. The first, your goal is to minimize cost function, which represents the error in the model's prediction. To minimize the cost function, in gradient descent, you start with an initial guess. That guess can be any number, 0, 1, fractions or whatever. You have to start with an initial guess. So this initial guess, you can then repeatedly adjust. I showed this last week when I was doing it manually, right? You repeatedly adjust these weights and you keep checking how the parameters or how the line that models your data points, how it matches up. And then you keep checking the value of the cost function. Now, for you to know how much or in which direction to adjust the parameter, you have to calculate the gradient like we saw graphically. So the gradient is the vector that points in the direction of the function's steepest ascent, as you can see. That is the point of the function's the steepness or the most steep direction of movement going upwards, right? And when I say going upwards, it's basically going in the non-optimal direction, right? So what happens is gradient descent will go in the opposite direction, and we've seen that already. And the reason to go in the opposite direction is that is how you minimize the cost function. You move the parameter in the opposite direction to the gradient, right, which is the steepest descent. So if the gradient is negative, you increase the parameter, you increase its value as you go positive. If the gradient is positive, you decrease the parameter, right? So at each step, the algorithm will calculate the gradient, and then it will take a small step in the opposite direction to the gradient, which is a negative gradient direction. The size of this step is determined by what we call a learning rate. This is very important. Remember I said when you calculate the gradient, if you want to just use the gradient, you might end up overshooting or even undershooting, right? And if you overshoot too much, you get to a point where you will never get um, the minimum or the minima. So you moderate how large of a step the parameter takes by applying a learning rate. A learning rate is normally a number that is less than 0. So it's a decimal number. So what it typically does is it reduces the actual value of the 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 jump or the increase, right? So when you apply the learning rate, you then apply that learning rate times the negative of the gradient. Remember, I said it has to go in the opposite direction. So you add that step, negative of gradient times learning rate, you add that step to the existing value of the parameter. And you continue this process over and over again, iteratively, until the algorithm converges. By that point, convergence in this case means that you get to a point where you cannot go higher again. Your cost function is at its lowest. It doesn't go up again, right? It just keeps staying in the same value, right? Or it just keeps going lower and lower. Typically, in most models, you probably never get to a point where the cost function, you know, how do I put it? Where it flattens out, right? In most cases, it keeps going lower. But once the cost function flattens out, or the loss or the error flattens out, then that means that that model has been optimized. It has converged, and you can no longer train it beyond that. That is gradient descent. So now, having understood what gradient descent is, the next thing is, how do we apply this gradient descent now to this same linear regression problem that we were trying to solve, right? That is a very important question, because remember, we just did it with the normal method, the normal equation we did before. But now we are going to run it with gradient descent. So the first step is we identify the linear equation, which we already know, y equals mx plus c. We apply the cost function or the loss function to calculate the error, right? And that error is, like I said, yi, which is the actual value, the expected value, or the the actual value, minus y hat I, which is the predicted value for that specific data point. You square that difference, right? You sum the squares of the differences, across all the data points. You divide it by the number of data points and you get an average, mean square error. This is the formula for it. We already did it last week. So that tells you how far your prediction is from the real Y. Now you want to minimize this error. So to minimize this error, the slight difference we will introduce here is that we will use gradient descent. So for gradient descent, you need to start with an initial guess, right? This is a visualization of gradient descent, which I've already explained. In most real cases, the loss function is not a single line with a minimum, it's a surface, right? Like you see in this three-dimensional rendering, and that surface is a gradient. You want to get to the bottom of this. Think of it like a bowl, and you want to roll all the way down to the bottom of the bowl. That is the point of minimal energy, right? If you're talking physics, it's also the point of minimum cost. So, so you have to start with an initial guess, because you cannot do this thing without initial guess. So you guess any number, take any number for M, take any number for C, right? So you start with that value. Sometimes we start with 0 for linear regression. But one thing I can tell is for neural networks, right? You don't use 0, because they will get into what we call common mode. They will just basically hang somewhere and they will not learn anymore. But yeah, you can start with a 0. You compute the gradient at that point. So for you to compute the gradient, you have to have an equation for the gradient. Now, the interesting thing is that all of these libraries, by the way, one of the most challenging problems in machine learning is the gradient problem. How can I calculate the gradient of a function? Most functions have their gradients, right? It's easy to calculate. But there are some functions, think of it like differentiation. It's basically a partial derivative, right, of that function. There are some functions that is really difficult. For those of us who did calculus, it's very difficult to calculate the partial derivative of it. But the nice thing is that libraries like PyTorch, right, and JAX recently, maybe TensorFlow added it, have what they call autograd. Autograd means they have figured out a way to automatically calculate the gradient of your function for you. So no matter what function you write, and when I say write, you are writing it as code with Python, AutoGrad will calculate the gradient of that function for you. So you don't even need to learn how to calculate gradient. But for the purpose of learning, we have to figure that out. So you will calculate the gradient of the cost function at that point for that value of M or C, right? When you do that, okay, that gradient will be either positive or negative. So that tells you which direction that you will use, to increase the loss. The loss increases if you go in the same direction as the gradient. So to reduce the loss, you go in the opposite direction to the gradient, which I've already said, right? So you choose a minus sign. So you are going to negate the gradient. That gives you the opposite direction. But you cannot just jump in whatever size. The size of the step also matters, not just the direction. If the size is too large, like I've already said, you can have problems. So you take a small step in the opposite direction. That small step, what you use to determine how small or how large that step is going to be, is what we call the learning rate. Very important. So once you do that, then you repeat this. So I'm basically saying the same thing again. Now, so we've done the cost function. We've done the model. The model is the linear equation, y equals mx plus c. That's what you're using to model your data. The cost function is the mean square error function, which is 1 over n summation of y minus y hat, okay? Across, sum across all data points. Now, this is the partial derivative of the cost function, or the loss function, which is del J del M, like we saw in the other slide. And if you do this del J del M for this value, it is actually very easy for you to see, for those who have done differentiation and integration. You bring this 2 down to this side, it becomes 2 times the everything in bracket, which is yi minus y hat. Okay, let's deal with this one. Let me do this with an annotation so that it will be easy for you to see. So we are going to just, first of all, in partial differentiation or a differentiation by parts, you will first of all take the outer relation, right? The outer one, which is this one. And for this one, it is 2 times whatever is here, right? That's the differentiation. So it will be 2 times 2 on 2 times okay, delta. So I don't have a delta here. Maybe I do, right? It's, yeah. So 2 times delta, that's not a very good delta, but to manage it, 2 times delta yi minus yi minus y hat. Okay, so let me just use a caret for that here. Okay, so that is the first part. But you also need to do this del y hat over, with respect to the whatever parameter it is that you are doing, right? Let's say it's m. So the del yi minus y hat del m is now you doing the the derivative of this inner one, or this inner one actually. So this whole inner one, you will find that yi doesn't depend on m, so it crosses off. Then you have minus mxi. So minus mxi depends on m, and if you differentiate it, you're actually going to get minus xi, right? So that will just be minus xi, right? And then the plus c doesn't depend on m either. Oh, I'm sorry. Yi minus y hat. Okay. Times m, basically. In fact, times minus m. So that because that's a derivative of that anyway. C doesn't depend on m, so it's 0, so it goes off. So all you have left is sorry, minus xi, should be minus xi. So this gives you minus 2xi into yi minus y hat. And that is the derivative, is minus 2xi into yi minus y hat. That is what that's what this is. That's what this is. Minus 2xi into yi minus y hat. Of course, divided by n, because that factor is still there out there. So it's minus 2 over n xi into yi minus y hat. That's the del j del m. If you do the same thing for c, you'll find that because c doesn't depend on x at all, so it's just minus 2 yi minus y hat. Summation is still there. Okay. So these are now partial derivatives of the loss function. You will now take these two equations and use it to calculate the gradient. This is basically the gradient, right? So when you hear gradient, this is gradient of loss function based on mean square error for m, right? For parameter, the first parameter, which is m. And this is gradient for C. C is what we call the bias, because it does not depend on, it's not the independent variable does not change, or y does not change with C, right? Y hat doesn't change with how do I put it? C is a constant. So however x changes, right? Y will always have a fixed value that depends on C. Then on top of that, you have the one that depends on X. So anyway, this tells us how much M should change to make the loss smaller and how much C. So this is basically the gradient. You will now take this gradient after calculating it, you negate it, and you apply the learning rate to it, and then use that to update. So that's the next step, right? The next step in your gradient descent process is updating the parameters. So you now update M. So the new M is going to be the old m, right, minus alpha. Remember, minus means negating, changing the direction, negating the sign of the gradient. Alpha is the learning rate. Del del m is the gradient. So with this, you have created an update, okay? And then the same thing with C. You adjust C by negating it and multiplying it, by negating the gradient rather, and multiplying the learning rate, okay? And you can even see the code for it is very, very simple. M equals M minus learning rate times dm. Dm is the gradient of the cost function with respect to m, and the c is the gradient of the cost function with respect to c. So you do all of this calculation. So for if you are not too much inclined, don't worry. I'm just giving you what we call first principles. I like giving first principles. That's why this course, this track is called Machine Learning Core. Core is a keyword. You are learning all the core things. You are, I'm essentially burying you a deep foundation that you will stand on, so that going forward, you will understand this and you can speak with authority about what it is. When somebody tells you what is learning rate or asks you what is learning rate or what is the gradient, you know what it means and you know what it is doing. So this is basically saying alpha is the learning rate. How big of a step should we take each time? If alpha is small, that means you're taking small steps. You will have slow learning. If you go to the gradient descent, you see like this one now is taking small steps, right? That is small alpha. Now, if your alpha is large, right, like this one, you can learn faster because you descend the gradient faster. You descend the the um what do you call it? The loss surface faster, right? But you are at risk of overshooting the minimum value because when you descend so fast, you jump like this, you can jump, in fact, with one step, two steps, you have jumped to the other side. And if you keep jumping with large steps, you end up never landing on the minimum point. You understand? If you keep jumping with large steps. So that's the danger. So it is something you need to take note of. So when we hear of adjust your learning rate, right, to match the size of the data, we're going to talk about all of that later on. So that is gradient descent with a single variable. Now I'm going to take some time out and do some code for that. So if you look at this now, if I let me do this from scratch so that it will be easy to understand rather than trying to use an existing stuff. It will be easier for me to explain, but I'll just copy the code across so that things will be fast. So the first thing I'm going to do is I'm going to create I'm going to create a function that will generate sample data for me so that it becomes easy to see how gradient descent will work when your data points are plenty. Okay, so yeah, so I'm going to do a separate code block for my imports. NumPy matplotlib. So basically NumPy is so make sample data is a function that generates sample data for me. And then I'm going to basically say x comma y is make sample data. So and then I'm going to print. So you will see the x and the y, right? You can see the x and the y. Now, the next thing I want to do is I'll bring in my mean square error computation. So this time I am using NumPy, right? Because I'm using NumPy, last time I was using a standard Python list. So I was kind of trying to use a clunky iteration using, least comprehension and all kinds of things just to do these calculations. But with NumPy, it is not hard to do that. I can actually just do something like x times 2, and it will give me, each value of x multiplied by 2, as you can see. So this is not difficult anymore. You see each value of x multiplied by 2 here, as opposed to what I had before, where I would have to look through it. This is a benefit of using NumPy, ND arrays. So I multiply x squared. This gives me the square of x. So it's very easy for me to now write a function that will compute the mean square error. And in this case, I just put y true, which is the actual y, and then the y pred, which is a predicted value. So this one is easy for you to see that I can just use NumPy and calculate the mean, right, of this, right? Y true minus y pred raised to power 2. NP.mean actually calculates the mean of the sum, right? So let me bring this in, and then I can actually do something like, let me just do compute mean, right? MSE of let's just use x as our this and y, right? So it will calculate a single value, and it gives you a float 64,273. So that you can see how easy it is now to use NumPy. Did you see me do any loops? There's no single for loop in this, and yet I'm dealing with a large data set. I can even plot this, right? If I have, with matplotlib pyplot, I can actually just plot a scatter diagram with the same thing, right? I can just say plot dot plot, right? With 0 as the data points, and it plots this generated data set. So already you can start getting the line of best fit, right? You can already start guessing the line of best fit. Now, I'm going to switch. I want to switch to, yeah. So you can already see the line of best fit, okay? Now, you can not see, but you can guess. With this, you can already start guessing. Okay, the line of best fit is basically in this direction. So it's very easy to tell already, right, what the line of best fit will look like. So the next thing I want to do here is I'm going to bring the loss. Okay, the loss function is there. I'm going to now bring the function that will calculate the gradients. And I'm going to take some time to explain that. Okay, so this is the mean square error function. I just tested it. This is plotting. And this is the function that calculates the gradient. So you can see we have the x, we have the y, right? And then we have the m and we have the c, right? So this is going to calculate the gradient of the MSE loss with respect to m and c for this model, which is y equals to mx plus c. So based on the function y equals to mx plus c and based on the MSE loss, remember the equation that we just did, and I explained it. The gradient with respect to m, the j dm is minus 2 over n times sum of xi times xi minus y hat I. That is each x and each y hat. And then the j, the c, which is the gradient of the cost function with respect to c, the c parameter, is minus 2 over n times the sum of yi minus y hat I. So this is what I had already shown. And maybe just for the purpose of making it easier for us to follow this, I'm going to take the formula, right? And I'm going to put the formula out here so it's easy for you to follow, because sometimes it might be difficult. As a matter of fact, um, let's put this in here. All right. So let me just take this, right? As a matter of fact, let me take the entire slide and just fit it in here so we can see. All right. Okay, so you see the slide, you see the equation. It's easy for you to see into yi minus y hat and sum yi minus y hat I. So this equation does this code does that basically. So we first of all get the shape. Shape 0. Shape allows us to count how many elements are there. So if to say x dot shape, right? This will tell you the shape of x. Remember, I talked about a tensor. X is basically a is one dimensional. So you can get the shape. You can see it's 20. It has 20 elements in it. A vector, it doesn't have a second dimension. That's why it's just 20 comma. And if you did y, you will find that y so the same shape. I don't know why this is taking. You see 20 for x and 20 for y. So by the time you take shape 0, okay, shape 0 is going to give you that. Then I hope it is better now. Can you give me a if it's better? Okay, so let me go back over what I just said. So the first line of code here, right? We've already seen the equations for calculating gradients. And then based on the equations, we now have this function that we are writing. And you can see the formula, right? The JDM is minus 2 over n times sum. And then the JDC equals minus 2 over n times sum. So these are basically the programmatic versions of these mathematical equations that have been typed out. So this is the implementation of it, right? Take note that this is just a comment to explain it. So shape 0 gives you the number of items. That's why I did this piece here, just to show you that shape gives you that this is a vector with 20 elements. Y also is a vector with 20 elements. So there are two vectors of the same length. So by the time you take shape 0, you are taking the first element of this shape, which is 20. So n will give you 20. Then y hat is now the model function, basically the linear equation that you are using to predict, right? And of course, you're going to pass in m and c, which is the current value of the parameters that we are using. So y hat is m times x plus c. Take note that this x is actually a vector. It's a vector. So let me even do something here just to prove to you, we are not dealing with scalars anymore, right? If you say m, let's assume, let's take m to have a value of 5 or 2, okay? Then we now do c, yes, c equals to 1. Then we can now say y hat, which is the prediction, okay, equals m times x. Let's just start with m times x first, right? And then we print y hat, okay? You will see that we already have a prediction for each value of x, we have a value of y. So you have, for each value of x we have, so we are going to have 20 values of y. In other words, we are doing what we call batch prediction. We are predicting for a batch of values. In a single line of code, we have calculated the prediction for 20 elements. Now, if we decide to add the c C does, the M and the X are, we use what we call broadcasting, which I talked about, vectorization and broadcasting. But be that as it may, right? You now have this as a value calculated. So you can see how y hat equals M times X plus C will give us a prediction. It will give you another new vector that is a prediction for each value of X based on the M that you pass into this function and the C that you pass into this function. Now you calculate the error. So you calculate the error by calculating y minus y hat. I can do the same right here, right? Just to show you how that works. So I can just say y, which is capital Y, minus y hat. And again, it's going to calculate the error for each one. This is not the sum of errors. This is just each individual error, right? By the time you now sum the errors, right? By the time you sum the errors, you now have the sum of the error. So if we were to do a sum, np.sum, numpy.sum of this, right, you will now get the sum of the errors. You get a single value, which corresponds to the sum of the errors. We can now decide to do sum of the square of the errors. If we wanted to calculate the cost function, like what we have up here, you see that we are actually calculating the square. So we square it first with this times 2. Times 2 is raised to power of 2 in programming languages, most programming languages. So times 2, right? So this gives you the square of the error. You see how large that square of the error is. Somebody who mentioned that, and that's the truth. When you're using mean square, you typically will have very large values error. Okay, so that's the second step of this function. You calculate the error. Then you now easily take this error and you fit it into these things, which, let me move this up because I was trying to explain stuff. So I think it's better. Yes. So you can now see we are now, instead of, we now do sum of X times the error. Remember, y minus y hat is the error. So you're just doing X times the sum of the error. Sorry, X times the error, then you sum it, right? And that's what you have, the X times error. Then you sum it. Then you multiply that sum by minus 2 over n, which is what we've already proven here. Minus 2 over n times the sum of X times error. And that gives you the dm, which is the gradient in M, gradient of J with respect to M. Okay? Same thing here, except this time you don't multiply X by the error. It's just the error alone. As you can see in this formula, it's yi minus y hat. So that is the error. Okay? And again, you take the sum of it and you multiply it by minus 2 over n, right? And that gives you the DC. So these are the gradients. So if I were to now proceed and do something like, okay, give me the gradients. The gradients will be gradient, okay, of X, Y. Let's say M is 2 and C is 1, okay? And I would calculate this. What will it give me? Okay, I did not define gradients, so I need to run this function to define gradients. Okay, now I run this, and you see I have two gradients, minus 113 and minus 16. So this already tells me, right? This already tells me that the gradient is negative. So that means I have to increase M. This is the gradient with respect to M, and this is this first one. And the second one is the gradient with respect to C. So this already tells me I have to increase M and I have to increase C. So that's the third thing. We compute the gradients. Now, for us to do the gradient descent, what I would now do is I can do this, iteratively, and I'm going to show you how I'll do that. So I'll do three things, right? I'll keep the graph here, okay, and I'll keep the graph last. I will now first of all calculate the cost function, okay, cost function. or error. So let's calculate error. Error equals what? So if you go back, the error is compute MSE of the true value versus the predicted value. So, oh, by the way, I need to predict first, right? Which I did not include. So let me add a prediction function. So that should have been the first. So I can just add that here, right? So the prediction function, which we can just call pred, given a value of x, you have to predict y, x, m, and c, right? You have to predict y. So this is simply y hat equals mx plus c. So it's simply m times x, right? Plus c. So this is how easy it is, to do that. So let me run this. So we have prediction of x of y for x m c. Right. So we start off in a by adjustment. So I'm going to start with a and c equals to 0, right? Yeah, well, let me do one each line, right? So m equals to 0, c equals to 0. So the error, the prediction is going to be what? Let's call it y hat. So y hat is going to be prediction of x given m and c. Okay. The error is going to be the loss, the MSE given y true and y pred. So y true is the actual value of y. So error is going to be compute MSE, which is compute a mean square error. The y true is y. The y pred is y hat. Okay. Then let's calculate the gradient. So the gradient is going to be gradients, right? Calculating x, y, m, c. I can now do a print and you say, okay, error and gradient, right? Then I can also do a print of x, okay, and a print of y. Okay. Then we will now also plot x, we'll plot x and y pred, which is, sorry, y hat, which is our prediction. And we're going to use line, and we're going to use, this should be blue. I don't know whether I should put the color first or, yeah, okay. So what I'm doing here effectively is, first of all, step one. Remember, we have mentioned that there should be 5 steps. Maybe I should make that as a comment here. There should be 5 steps in training with gradient descent, right? So step 1 is calculate the predicted values. Then to calculate the loss function, the error, right? Using the loss function. Then calculate gradients, right? Then the last gradient and learning rate. Okay. These are the 4 steps. So the first step, I calculate the predicted value y hat. The next step, I calculate the error. The third step, I calculate the gradient, right? I'm printing, I'm plotting. I've not done the 4th step yet. We'll come to that. So I run this and you can already see the dots. Okay, let me flip the colors. Let me flip the colors. Yeah, let me use red for this. So because we started with 0, 0, like the line, the model predicts this line, which is very far from where we want it to be. You can see. Now, if I want to calculate the error, you can see the error is 499. It's really large. You can see the gradient. The gradient is let me do a /n so that this separates everything. Let me also do a /n here and here. Okay, so the x, these are the values for x, and these are the corresponding values for y based on m being 0 and c being 0, right? Well, that's interesting because uh, there's something wrong. um, okay, this is y. Okay, I did not print y hat. Okay, so let's print y hat as well. Okay, y hat. Let me see if I can get the hat in the y. Yep, I can. So y hat will be y hat. Okay, so this is the interesting thing. So this is x, this is y. You can see y hat is all zeros, and it's very easy because the m is 0, the c is 0. So basically made everything 0. And that's why the line is just a straight line at the 0 value of y. It's a very poor predictor of these data points. So it's a poor model of these data points. Now, the next thing I would do is based on these gradients, right? Let me do a manual adjustment. I'll do a manual adjustment the first time. Let me say I pick a learning rate. I say, okay, learning rate, LR is the learning rate is let's just say 0.1. So 0.1. Okay, we want to make small steps. Okay. Now, the value. Oh, by the way, let me pull these ones out so that I can run this iteratively. I hope my network is not so bad that adjust the parameters. Okay, so remember when we are adjusting the parameter, we're saying the m, you change the direction. So you take the old m, you subtract, it has to be minus learning rate, okay, LR, times the first value of the gradient, right? Which is the change with respect to m. So that's grad 0. Then C also is the initial C or the current C minus, again, because you are changing the direction of the gradient, minus learning rate times the gradient. So you now have these updated parameters. Of course, these updated parameters will not be printed. They will not be they will not be they will not be used for the plot, but in the second iteration, they'll be used. So we run this. You can now see that we have updated parameters now just by applying a small learning rate. The updated parameter, we now have M changing from 0 to 26 and C changing from 0 to 3.88. And you can even go check out what will now in the next iteration. So in this iteration now, and C, let me put this in, let me put /n as well. We will see it properly. Hello, give me a thumbs up if you can still hear me. Right. So you can now see with the new M and the new C. Hello, can you hear me? Okay, maybe I might have to switch to a better network. Okay, so what I was trying to explain is what happens in gradient descent. So at this point, we have updated the value of M and we have updated the value of C. So you can see that M and C, the new M and the new C is now giving us a different line. This is now a new version of the model that has learned a little bit, but it has overshot. Like I said, sometimes if you do too much, you overshoot. So you can see it is now overshooting in the opposite direction, in the in the reverse direction. We're not getting the optimum, we overshot the optimum value, right? In fact, as a matter of fact, I wanted to plot a graph of the learning curve, sorry, of the gradient descent curve, so that you would see how the optimum values are, you know, moving around, right? But yeah, okay, so now this is the second iteration. You can see this error is really big. It's blowing out of proportion. Now, if I run this again, you can see it swings again in the opposite direction. Now the swings are getting larger and larger. And this is an interesting thing to learn because this is really what happens in real life. If you don't choose your hyperparameter well, and this is now the first hyperparameter, you will find that it is not converging anymore. It is diverging. You can now see that the M and C is increasing. It's now 804,118, and the curve is getting out of whack. It's getting worse, right? It's getting worse. So in this situation, what do we do? In fact, what I would like to do is, apart from plotting this, I would like to plot the gradient against um the gradient of um I want to do two plots. So I'm going to do a plot. Yeah, I'm going to switch network. Second. Hello. Give me a thumbs up if you can hear me. Okay, so I'm adding a subplot, a bunch of subplots to this plot. What I'm trying to achieve here is to allow us to see how the points are jumping around the loss curve. So we have the first subplot, which is going to plot the actual values and the model, the line that predicts. Then here I am going to create the M's and the C's, right? And then I'm going to plot that. So I will do, for us to calculate, we need to calculate the values of M's and C's. Okay. And the errors that correspond to, well, okay, so in this case, right, let's just plot only the errors. I'm not going to worry too much about, yeah, so let's just plot the errors against itself. So let's just do errors, and yeah, okay, and then we will show the plot. Okay, so I'm going to start this again from here where the learning rate is still 0.1. The M is 0, C is 0, right? Then we do the first one. So we get our first plot. So you can see this is the first plot of the error. You can see that the error we have is 499.6. So that's why we have a plot for this value of 0, which is basically the starting point. We have error here at 500. Now, we don't do the minimum point. We could actually plot the minimum point. So we can plot that by plotting the gradient. Okay. I would like to plot the gradient curve for different M and C. But let's leave it at this for now. If you actually plot the gradient curve M and C versus various values of M and C, then you would see how the error looks like, the gradient error curve looks like. So let's see if we can do that. We can actually do sorry, not the gradient, the loss curve. So we want to plot the loss curve as well. So what I will do is plot yeah, we'll need to have a y hat. So let's just have y hats so that we can use that to compute okay. This might be a bit complex, so let me leave that out for now. All right. So in the first iteration, the line is down here and our error is almost 500, 499.6. In the next iteration, you now see that the error has jumped up to 17,817. This line is much worse. In fact, this line is much worse. And you can see this has jumped to this other end, right? The new loss value. Then we run it again, the third iteration, and it now swings the opposite direction. It's very low, a very bad curve. The error is now 639,000. So you actually see that the error is increasing. The more we run it, the worse the error becomes. Right now, the error, so this is not converging, this is diverging. And you may ask yourself, okay, if I were to even plot this as a line, you would see that it is exponential. By the next time you run this again, the error will probably become out of range. You see. So this is not diverging. So when you have this kind of situation, what does that mean? It means that you were taking too many jumps, right? It means that your jump was too big. Your jump size was too big. So if your jump size is too big, let me ask a question. Now you can type your answer in the chat. What should I do to reduce the jump size? Whenever you see it diverging like this, and it, instead of the error becoming small, it becomes larger. What does that mean? I would like to see your comments, right? What do we do? Yes, the learning rate is too high because the learning rate is the factor that you now see the value of the learning rate is a factor that you can use to reduce divergence. So we will reduce the learning rate a little bit by just by 10, divide by 10. So it's 0.01. Okay. It's now 10 times, it's now going to take 10 times lesser jumps. And we'll try this again. Okay, so now let's see what the error is. It still starts with 499, of course, because we've not done any adjustments. And we still start with a 0 point and this point here. We now run the next iteration, right? So this is now manual iteration. You can now see with a smaller learning rate, it did not jump too far. It comes closer. And you can see the error is now 48. It's now 48. And you can see it is now coming closer, to the point of convergence, the minimum point in this loss curve. I did not actually plot the loss curve. I really wanted to do so, but that would take a bit more time. Now, I run again. You can now see it is coming even closer to what we want, right? We have now seen that it is adjusting. We have reduced the learning rate and it's adjusting. And now you can even see the loss curve is coming closer, right? By the time we run it one more time, right, you can now see how it is adjusting. At this point, you will find that the error here is 3.3. With this error, you would see that, we can even plot the gradient curve. So the next time I'm going to plot this gradient curve, I'm going to use a red line. Or maybe I'll plot another one. Let me plot another one. But I'll use a blue line. All right. So I'll plot with a blue line so that we can see how it goes. So now you can see it comes really close. And because you have tuned, so this is what when we say tuning hyperparameter, you see the difference between you training, the training, you are not the one adjusting the parameter now. I didn't adjust the parameter. The formula adjusts the parameter because it is now a formula here to adjust the parameter, right? So this formula is slowly, you can now see the error is 3.0. You begin to see that this error, at some point, this error will basically flatten out and it will not be. So I run again. Now the error is 3.002 and it will not get any because the gradient descent is essentially assuring that it gets to a minimum. So this is very important. One of the things you will learn quickly is that, if you don't tune your hyperparameters well, things jump around. Now, all of this, I'm doing it manually, running it one iteration at a time, one iteration at a time. Now, my error is 2.99. But is this how we normally do it? No, of course. I will put this in a loop and it will run in a loop. But the thing is that when you run in a loop, you need to work out what we consider a stopping condition. When do I stop? When do I say I'm okay? So one of the simplest stopping conditions that we normally use is the difference between the previous error and the current error. You can give it, okay, the error doesn't change by a certain value, right? Stop. But there are some times when the error may never really change by that much. So it can keep running infinitely. In fact, I can actually take this whole thing, right, and just put it in a loop, right? A simple while loop, right? While, so let's just say while true, okay? So this time around, let me plot after the training is done so that I don't flood. So I'm going to basically take all the prints and you can now see that if I remove all of these other things that are not really part of the if I remove all these other things, right, that are not really part of the okay, maybe I can put the updated parameters in here. But yeah, these other ones are it's just me printing final values. So I'm not going to print them inside the loop. This is after everything I can plot. Of course I would, oh, okay, I still need to add the section where where I, I append. I also need to do this inside the loop values. So one of the important things is that you need to keep tracking your parameters as they change, or your not parameters, your evaluation, factors, the metrics that you're using. So in this case, I'm just using error first. So I'm appending it, so I'm keeping track of it. So that at the end of the day, I can plot all of them, right? So with this will run and it will never stop. So I have to stop it manually. Probably can stop it manually. Okay, so I stopped it manually. Um, yeah, I stopped it manually. So it's a keyboard interrupt. But if you can now see, because I did not calculate the errors or anything, let's just run it. There are ways you can do this, right? One way is you can say, okay, let me run it for 100 iterations instead of running it forever. Okay, so I could say while or you can just say for this in range, let's say 10. I want to run it for 10 iterations. That's all. Okay. So but let me start again from 0, right? I run it for just 10 iterations. Okay, so it's going to plot this, and you can see the 10 iterations. This is how the lots drops over the 10 iterations, and we don't have this, function. As a matter of fact, if I really wanted to be, I could actually plot each the how this thing progressed. So that's why I keep the M and the C. I can do a I can do a loop to plot this. So I can do something like for in range. Again, I have 10 iterations. So I have 10 eyes. Okay, so let's say for M comma C in not instead of range 10, I can say zip of M's and C's. So I pull out all the M's and C's. Um, I can now basically plot X, Y hat will be pred, um, right, pred. So I'm going to use X, yep, and Y, and I pass in the M, sorry, X, and I pass in the M and the C. So this will basically plot, make a, a plot for each of the previous versions of this thing. So let me run this again and then run it for 10 iterations. And okay, I'm not getting what I was hoping to get. Let me take this out into a separate code block so I can control my code blocks properly. Okay, so let's start again. Again, so I start with learning rate, these errors. So after each epoch, so this is basically what we call an epoch. I print the parameters, and then here I want to plot everything. So yeah, this doesn't change. Okay, so let me make this MI and CI. So for some reason I have Well, I guess it's the difference. hmm, Um, hold on. Let me put this in before adjustment. I think that may be the issue. Let me add them before adjusting. I only added them after adjustment, so I lost the first value, which is probably the most important one. Okay. Well, it almost looks the same.
Hello, sir.
So
You are appending MS and
I'll
MC. You are not
debug that
appending.
later.
Hello, you are not appending the MI that you are looking through. You are appending MS and MC. Go down to the third code, the next code, sir, where you are zipping. Inside after the zip, yes, the zip. What you are printing is MS and MC. You are still printing MS and MC. I don't know if
Oh, the loop. Okay, yeah, okay. That's correct. Okay, and what I am predicting with is M and C. So MI and CI. Thank you. Okay, so let's run this again. Okay, so now let's see if I can get what I really wanted. Right, this is what I wanted. So I wanted to show how these lines kind of progress. Um, maybe I can use a single instead of okay, this is not what I want. Yeah, so the colors would change, but I want the lines to be maybe dot lines. So yeah, so the M's are changing, which is what I was looking for. I think there was a bug in the code. All right. Okay. This is not what I was expecting. Um, okay, this is not a valid, not valid. Okay. Well, let's just okay. So what I was trying to illustrate was how the model starts from this 0, 0 line and it just slowly comes closer and closer. And you see, as it gets to this point, it gets closer and closer. And it never really goes beyond this point because at this point, the minimum point, it converges, right? I could actually run this for another 100 epochs, and you can even check the errors, right? The errors basically did not change much. I could run this for another 100, epochs, and it's not going to change. So this is what gradient descent does, right? I know this is taking longer than I planned. You see, at this point, this is basically they are just all crowding. This is the minimum error. You cannot get any better than this. And if you go and look at the value of that minimum error, it's about where is it? Um, well, it's okay, it's 2.868. Okay. So this is convergence and this is gradient descent with sorry, linear regression with using gradient descent. So let me now just quickly round up because we still have to look at linear regression with multiple variables and logistic regression. So, but due to the time constraint, I'll probably just leave this till next week for us to complete. But by way of introduction, when we are talking about linear regression with multiple variables, okay, what we are now doing is, rather than do our regression, using a single value of x, a single independent variable, we are now doing the regression using um, using an array of x's. So, for example, you have y equals x1 plus x2 plus x3 plus x4 plus c. So instead of the value of y depending on just one x, it depends on it. Instead of having one single independent variable that determines what y is, you have more than one. You can have two or more. That is what we call linear regression with multiple variables. And it's a statistical method. It uses two or more independent variables to predict a single dependent variable by modeling their linear relationship. So it's a linear relationship. Now, in this situation, each value of x has a coefficient. So in this case, we are using beta as a coefficient. Each of these beta determines the value of y, or how much x contributes to the value of y, right? So for x1, beta 1 determines how much component of x1 will affect y. Beta 2 will determine how much component of x2 will determine or will affect y, and so on, up to n number of x's, right? So beta n determines how much component of xn rather, affects y. So it's a sum of the individual contributions of each of those independent x's, or values of x, that contribute to y. Then we also have beta 0, which is a constant. There is no x on this because it always affects y, no matter what values you have for each of the x or x's, right? This beta 0 corresponds to the C that we have been using, and the beta 1, beta 2 correspond to the M's that we have been using, each for each. Then you have this thing at the end we call epsilon. Epsilon is an error term, right? Which, well, this is a generic thing. Like, there are some random variations that may happen, which the model cannot, is not explained by the model, right? So for now, ignore this epsilon. We can talk about it later. But this is multivariable linear or multiple variable linear regression. And when you are solving it, you use exactly the same method that we are using here. The only difference is that now we will calculate the contribution of each x. The main difference is when you are doing the we'll come to all of this, but when we are doing the gradient, right? So let's look at the gradient for a single variable, right? So when we're doing the gradient, we did a gradient with respect to m. It was this with c. Now, when it is multivariable, all you have is that instead of having only one m, you have multiple m's. You have m1, m2, which is beta 1, beta 2. It's the same thing. It's just letters that you use. So you have m1, m2, m3, m4, and so on. So you will now do each of the m separately. dj d m1 equals minus 2 over n x m x m1. That is the x that corresponds to m1, right? Times yi, which is the prediction, sorry, which is the actual, minus y hat, which is the prediction. So it's going to be exactly the same thing. The only difference is that here, for each m, you calculate its own contribution by using the x value that corresponds to that m. So if you have 10 m's, you have 10 features, and m now, sorry, the x, each x, the x corresponds to features now when you talk of and hear of feature engineering. And we're going to look at how that correlates. So each of those features can now be mapped into its own gradient, its own contribution. You use exactly the same formula, because in this case, you are still going to use a mean square error. And then this last one, you still use it for beta 0 or C. Basically, the constant factor always uses this. And we can then expand this method and use it for multiple variables. So that, for example, when they say predict the cost of housing in a particular town based on so and so factors. Now, in the case of a single variable, it would have been something like predict the value of something based on one factor. But now we have multiple factors. So those multiple factors, each of them is a variable, an independent variable. Each of them will have its own coefficient or m, right? And each of them will have its own gradient. You still sum together the gradients, right? You still sum together them to make the cost function. You still sum together to do the prediction. But when you are doing the update of each parameter, you use each one's own gradient. So just think about it that way, and you have already solved it. So I'm going to jump ahead, and I would like everyone to do a bit of research. The task I'm going to give, I will ask you to do gradient descent with single variable, and then you are also going to do the gradient descent with 3 variables. Okay, so I will end at this point, and I'll stop the call. So if there are any questions, we will take them after the recording.